When the first dinosaur appeared, some 230 million years ago, it was a small, speedy predator. The entire dinosaur family, which ruled the Earth for the next 165 million years, was born of this small beast. Early in its evolution, two separate lines of plant-eating dinosaurs appeared. How they evolved from that first carnivore is still an unsolved mystery. Over 100 million years after this first dinosaur, during the early Cretaceous period, a group of predatory theropods would begin this same incredible metamorphosis, from meat-eating to plant-eating. The missing link of this passage has just been uncovered on a Utah mesa in a mass grave that contains hundreds, possibly thousands of skeletons. The bones of the newly found species, named Falcarius utahensis, traces the journey from meat-eating predator to lumbering vegetarian. In a barren Utah wasteland, a group of scientists is journeying back in time, 125 million years. What they are uncovering may change what we know about dinosaurs forever. Dino expert Jim Kirkland and his dedicated crew battle searing 100-degree temperatures as they pick, scrape, and claw into a vast pit of horrors, a dinosaur mass graveyard.
If we're conservative, we can guess that perhaps there's 1 million bones of this animal within this area. That's a pretty extraordinary sample. Most dinosaurs are only known by a few bones, a partial skeleton from one individual. Here we're going to understand a population that we believe was probably killed about the same time.
The Discovery Quest scientist is a veteran dinosaur hunter who has discovered numerous new species, including the most dominant killer of the early Cretaceous period, Utahraptor, and the first therizinosaur ever discovered in North America, Nothronicus. Now, this new find promises to be his biggest ever.
We're very fortunate in this site. We have so much skeletal material from babies to adults. We have every element of the animal represented except for a few parts of the front of the skull and the front of the jaws. It was an animal that probably reached about 3 feet at the hips, walked on its hind legs, had a particularly long tail, got large forelimbs with large raptorial claws. Basically, even for an animal with 3-foot hip height, this thing could probably palm a basketball with its large hands. An elongated neck and a fairly small, elongate head. Particularly interesting in this is it's got very tiny teeth. This thing has probably over 100 teeth, and these tiny teeth were not what you would expect in a typical meat-eating dinosaur. This group of animals is thought to be classically plant-eating animals. This is one that is so primitive it might be in the transition.
Falcarius is literally caught in the act of evolving from a predator into a plant-eater.
The thing that really struck me about this site and the animal once I saw the teeth and the vertebra was that we had a therizinosaur, an animal that's best known from Asia. Only a couple years earlier, a fellow by the name of Doug Wolf and myself, we described the first therizinosaur ever found in North America. And that was pretty exciting. We were charged. And then just a couple years later, we stumble onto this animal. Yeah, look at that. And this animal is much, much older, perhaps the oldest one in the world. We have the biggest collection of material from this animal of any specimen anywhere in the world.
It is a find Kirkland was grateful to get. It was a private collector who discovered this valuable dinosaur graveyard on federal property, land previously surveyed for fossil sites and then passed over.
The site was discovered probably in the very last part of the 20th century by a fellow from Moab out looking for agate by the name of Larry Walker.
This is the hole that I dug into the hill. I worked on my side and excavated the bones with a small tool. So after excavating and bagging these fossils, I would take the pieces home and reconstruct the individual bones.
Walker sold the bones not needed for his skeleton on the black market. With close to 2/3 of a complete animal, he realized he had a new species and made an important decision.
And then that's when I decided to turn this over to the state of Utah and live with the consequences of my decision.
Walker contacted Kirkland, but even with the coordinates, the experienced Utah state paleontologist was unable to find the elusive site.
When we first came out here, we would never have found this site if Larry hadn't taken us right to the site itself. We got the coordinates, went out here, missed it. So we were walking on top of that surface, just out of sight of the quarry, looking for the site and missing it completely. If Larry Walker hadn't taken us right out here and put our nose on these bones, we would never have found this site.
I was investigated, I was indicted, I was convicted of theft of federal property. Consequently, was given a 5-month sentence with 3 years probation and a restitution amount of $15,000.
Walker's decision to turn the site over to Kirkland was personally costly, but if he hadn't come forward, this important discovery would have remained buried in the Utah desert. Lindsay Zano understands how important the discovery of Falcarius is. She is a doctoral student at the University of Utah, specializing in therizinosaurs, the group of dinosaurs Falcarius gave rise to.
Therizinosaurs are a truly bizarre group of animals. They've been mysterious ever since their first discovery. The first discovery of a therizinosaur was made on a joint Russian-Mongolian expedition in the 1950s. What the scientists found there were these giant, blade-like, 3-foot-long claws, and the only animal they could think that that could belong to was a giant sea turtle.
They were wrong. 40 years later, the Mongolian desert provided the true answer. The 1993 discovery of a nearly complete therizinosaur gave paleontologists the proof they needed. Skeletal similarities identified this bizarre group's place in the dinosaur family tree. Therizinosaurs evolved from meat-eating theropods. As the oldest known therizinosaur, Falcarius shares many characteristics with its predator cousins.
We now know that therizinosaurs evolved from a group of dinosaurs known as raptor dinosaurs. Most people are familiar with them through the velociraptor in the movie Jurassic Park, and they're the only group of dinosaurs that still exist today in modern birds.
The raptor was the smartest, quickest, and most dangerous dinosaur of the Cretaceous period. Alone or in a pack, it was well equipped to deliver a lethal blow. Raptors possess speed, killing claws, and serrated teeth. Falcarius shared their forelimbs and swiftness and provides the missing link between raptors and the full-blown plant-eating therizinosaurs. 90 million years ago, Nothronicus appeared. The size of an elephant, it towered over its raptor cousin. It had the claws of a killer, but its small head and long neck belonged to a plant eater. It looked like a half-plucked turkey and walked like a pot-bellied bear. Therizinosaurs such as Nothronicus were rare in North America. They were long thought to have migrated from China. Now, its direct lineage has been uncovered in the Utah desert.
With the discovery of animals like Falcarius that preserve the primitive forms or the ancestors of these later, more strange-looking animals, we're able to determine who they're related to. I have 2 members of the group. I have some casted material from the primitive therizinosaur that we've been digging at the Crystal Geyser Quarry, and I have some casted material of Nothronicus, which is a therizinosaur that's more derived that occurred later in time. And you can see there's a huge size difference here. These are both
the scapula of Nothronicus is 3 times the size of the more primitive Falcarius.
There's a lot of changes that occur in the skeleton between the primitive forms and the derived forms. Some of those things that we can illustrate are in the shoulder blade. This is the articulation with the humerus, which is pointing downward in this animal. In some of the later therizinosaurs like Originated, we see movement of this joint that associates with the humerus here, and we see that this animal had the ability to raise its arms higher than the more primitive forms, which may have something to do with how it was acquiring its food.
Falcarius provides the key to understanding how this bizarre group of enigmatic plant eaters, known as therizinosaurs, evolved. More importantly, Falcarius is the link to how a group of small, fast, and vicious meat eaters changed into large, slow, lumbering plant eaters. The clues lie in the million bones buried deep within these rocks. But can they answer all the questions about these mass deaths? What caused Falcarius to die in these huge numbers? What attracted them to this particular place? These are just some of the questions Kirkland's team hopes to answer as they search for clues in this dinosaur graveyard. Don DeBlue manages the removal of these prehistoric remains.
Well, here in the dig site, we have about a meter of bone-bearing sediment, and the bones are distributed pretty evenly throughout that meter. And we use our little picks to just kind of push gently through the matrix until we hit one of the little nodules. You can feel that. Then take the brush, sweep that away, put it into our bucket.
Many of Falcarius's bones are encased in minerals.
This lightish brown color is the carbonate nodule. This darker brown and black is actually the bone sticking out of the nodule. Occasionally we hit some nice little things that don't have a lot of nodule around them. In this case, there's a beautiful little toe bone here of a juvenile animal.
Because this Falcarius toe bone is not encrusted in rock, it is quite fragile. Glue is used to help harden it.
A few drops of that on there.
Layer by layer, every bone fragment from this massive graveyard becomes a new piece of evidence.
The small nodules we can collect, just wrap them up in toilet paper. Some of the larger things we'll use the medical bandage to make a little gypsona jacket around it.
Back at the lab, these fossils become the clues to solving the mysteries surrounding the life and death of Falcarius.
Voila! The inside of the grid should be the meter line. So if it's under the metal, it's just outside the grid.
Just outside the grid then?
Using a grid, Kirkland's team records each bone on a site map. This places each fossil in its unique position, an essential tool when sorting clues in a graveyard that may contain 1 million fossilized fragments.
All right. See that little nodule? Right down there.
It is time-consuming, and it's not for everybody. You know, it's very tedious work.
That's not worth nothing, is it? Neither's that.
The neat thing is as I push this needle through and I hit something, you know, that's never been seen by anybody before. It's been buried here for 125 million years. It's just another piece of the puzzle to help put this animal together, our knowledge of what it was like. So really, I think it's the discovery that keeps you going.
These graveyard bones hold many secrets, but they aren't the entire story. To understand why all these animals died here and why these bones were preserved when most of this time period was not, it's necessary to look beyond the fossils. The Suarez twins from Temple University found evidence of a spring by looking at the rocks.
It's like telling a story. It's, you know, using the rocks to tell a story. So not only are the bones important, but the rocks that the bones are found in are important. That's the reason why we stay looking at the rocks. You know, we look at dinosaur bones are really pretty. Oh, they're very pretty. And we love them. We love them a lot. But the rocks are also, they tell the story, a part of the story that sometimes the bones can't always tell us. So the top layer that we saw was the initial piece of evidence that pointed us toward the spring deposits. And then the other deposits that we found were the bones, were the rocks that were at the base of the quarry. And these rocks have very similar aspects to the modern spring deposits that we see at the Crystal Geyser. This piece here is a young modern deposit. The radial structure that you see of the crystals moving away from the center is also seen in pieces of this rock.
One of the theories that's been proposed for why the Crystal Geyser dinosaur quarry was preserved, and one that I kind of like myself, is that it was preserved by a coating of carbonates laid down by a spring deposit. I like to tell people it was a scab on the erosional surface that preserved the bones in place.
The modern Crystal Geyser spring is coincidentally located near the Falcarius gravesite. It vividly demonstrates this theory.
These are the kind of minerals that we see preserving the bones, calcium carbonate encrusting the bone. What we have here are somewhat older spring deposits on the order of thousands of years that have been exposed by the Green River cutting through them. Some of the carbonates that were studied by the Suarez sisters have some similar features, and it's one of the lines of evidence they've used to suggest that spring deposition may be an important part of why this quarry was preserved where it was.
The slide that I have on the screen right now is approximately 125 million years old. These are rocks that we found at the Crystal Geyser dinosaur quarry. And then the slide that I have on right now is a piece of the modern Crystal Geyser, probably no older than 1,000 years old. So when you look at the different crystal structures, they look pretty similar, and that's how we've been able to put together a little bit of evidence to determine that the Crystal Geyser dinosaur quarry was deposited either in or near a spring.
The same deposits that preserve the bones in the dinosaur graveyard must now be carefully removed in the lab.
When we discover a fossil in the field, the first step is to make a plaster jacket to protect the fossil so that we can bring it back to the lab. Once it's at the lab, we saw apart the jacket, revealing the fossils entombed within the rock. And then we have preparators who spent hundreds of hours carefully detailing, removing rock, or what we call the matrix. And we slowly chip away the rock, revealing the bone within it.
Tom Millithan is chipping away on the Falcarius fossils at the Utah Geological Survey labs.
The first thing we do is we take the bottom of the field cast off, and then we start working down through the matrix till we start hitting bone. You can see right here, I'm starting to hit bone.
The rock or mineral which surrounds the bone is known as the matrix. This material must be painstakingly removed using dental picks and small drills.
And when the matrix is too hard to get off, we have to use another solution. We acid etch it. This is the portion that we're trying to acid etch off to get the matrix off and get down to the bone. And you can see here where we've actually, the acid has etched it down, and you can start seeing the bone, and we can start working on it.
After carefully cleaning the bones, scientists are able to view them in their entirety.
Over 95% of fossils that are collected in the field end up in the museum collections out of public view. This is where scientists who are doing research on animals come to compare the bones they've found in the field to bones of known dinosaurs and other animals that we keep in museum collections. For instance, when we find the claws of Falcarius, we might come to collections and compare them to other meat-eating dinosaur claws that we know of, such as this thumb claw from Allosaurus, or a claw from one of its closer relatives, one of the raptor-like dinosaurs.
Comparing the bones of Falcarius to other animals is the first step in a lengthy investigation. Every bone is carefully examined for clues. Within the fossils of this primitive therizinosaur, the transition from predator to plant eater is waiting to be found. Bone by bone, Falcarius reveals its precious secrets. Some of the answers to the mysteries surrounding Falcarius can be found in the time it was living. During the early Cretaceous era, temperatures were rising, and so were sea levels. It was a period of remarkable change.
It wasn't until the early Cretaceous that one group of carnivores evolved to be probably, as far as we can tell today, herbivores. Falcarius, though, is a true missing link. Here we have an animal that allows us to tell the story of how we went from a velociraptor-type predator to something that was a large-bodied, full-blown plant eater. Now, another interesting thing is going on in the world at this time. Flowering plants are appearing for the first time and really starting to take over. And it may be that this spread of these new plants helped to lead to the evolution of Falcarius, this predator turned herbivore.
The discovery of Falcarius provides a unique opportunity to see what features this early therizinosaur preserved from its meat-eating ancestors.
So how do we know that therizinosaurs evolved from raptor-like dinosaurs? When we find an animal that's primitive like Falcarius, we're able to look at its anatomy and see things that have been retained from its ancestors. For instance, in the case of Falcarius, which represents early therizinosaurs, we're still able to see predatory features like sharp claws. In the case of raptor dinosaurs, folding arms. This is the forelimb of Falcarius. One of the things that's easy to recognize about it is that it basically looks like a raptor dinosaur. It's long, it's elongate, the bones are not thick and robust. The claws are still predatory dinosaur claws. There hasn't been that much change in the forelimb.
When we look at the legs of this animal, one of the really significant features we see with Falcarius is the lower leg bones are significantly longer than the upper leg bones. These are features we see in running animals. It's a real character of all the Maniraptorans, Velociraptor, the Oviraptors.
The sharp claws, long forelimbs, and fast running capabilities all trace back to the raptor roots of Falcarius.
All later therizinosaurs that we know of have femurs that are longer than the lower legs. This is a sign of an animal that's moving much more slowly. In addition, this animal still has a pretty typical theropod three-toed foot with 3 functional toes, but the little dew claw here in later therizinosaurs becomes larger and actually becomes a weight-supporting toe once again.
What makes Falcarius unique in the fossil world is that now, for the first time, scientists have a missing link, a step in the evolutionary transformation from a predatory raptor to a plant-eating therizinosaur.
One of the things we know you have to do to build a therizinosaur is to take a velociraptor-like animal and give it a huge gut and shrink its legs down, add a couple extra toes, and lengthen its neck and shrink its head and give it small leaf-shaped teeth instead of those sharp blade-like teeth like a predatory dinosaur would have. Previously, we had no real information on how this transition was happening. With the discovery of Falcarius, we're able to take an in-depth look, sort of a time slice in evolution, and take a close look at what areas of the skeleton are changing.
When we look at the hip region here, we see some features that are very important in the therizinosaurs that are developed much more so later. They begin to flare the hip out laterally, pull the bones at the base of the hips back, basically creating a large basket to support the digestive system that a plant-eating animal needs. And this has already begun to do this, and there's really not much reason you would start expanding your abdominal cavity unless you were going to process something that was more difficult to digest.
In a unique twist of evolution, Falcarius represents a meat-eater forsaking its bloodthirsty ancestry as it becomes a vegetarian.
Well, if we take a look at this meat-eating dinosaur that would have been a close relative of Falcarius, you can see it has sharp blade-like teeth that would be serrated like a knife. If we look at the teeth of Falcarius, you notice they're smaller, more densely packed. They're not serrated the same way that the meat-eating teeth were, and they're leaf-shaped, so they're much better suited for eating plants.
The enlarged gut and smaller teeth were directly related to the change in diet that occurred with Falcarius. Other more subtle changes were just beginning.
And then as a really exciting feature, we see this specialized elongate neck. Now, as you look at this neck, it looks heavy, but the bones are full of air sacs, and really none of the bone in this neck is more than 2 millimeters thick. If you filled the dry neck bones with helium, they'd probably float. Now, for Falcarius, we had hundreds, thousands of bones all mixed up in the quarry. And when we describe an animal, we have to pick one bone to make the type specimen, to define the species on.
And for the case of Falcarius, we picked a bone that had lots of different features to it. You want something that has a lot of parts you can describe. And for this purpose, we used the brain case. Now, the very distinctive feature for Falcarius that we don't see in any other dinosaur are these very large excavations all around the base of the brain case that actually overlap smaller little excavations. This is where air sacs, such as we see around the brain case of birds, are coming in and surrounding this part of the skull. This might have been used for cooling, it might have been for lightening the head. We don't know why in this particular animal, but they're very distinctive.
These air sacs weren't the only feature Falcarius had in common with birds. It probably had feathers. Modern evidence shows that small predatory dinosaurs and modern birds have over 100 similar bony features. Dramatic evidence was provided with the 1995 discovery of a dinosaur ecosystem in Liaoning, China. This site, which was buried by volcanic ash, contains many pristine fossils with primitive feathers.
One of the other bizarre features of therizinosaurs is they were probably covered in feathers, not the flight-like feathers that you think of in modern birds, but the more downy feathers that you think of sort of keeping a duck warm, sort of what we call proto-feathers. We know this because the ancestors of therizinosaurs were feathered, and we know many of their descendants were. We also have a feathered therizinosaur that's from China, where they have a dramatic assemblage of feathered dinosaurs in a really remarkably preserved ecosystem. Feathers, although you might think evolved specifically for flight, obviously are serving other purposes in feathered dinosaurs. Because we have such a vast diversity of feathered dinosaurs, it leads us to the question, what other purposes are feathers evolved for? Some of the things that come to mind are color, camouflage, for attracting mates, possibly for thermoregulation or staying warm.
In addition to looking at the specific changes going on with Falcarius' skeleton, understanding what other animals it lived with helps complete the picture of its environment.
Of the more than 1,000 bones cataloged so far from the Crystal Geyser Quarry, more than 99% of them pertain to Falcarius, our new dinosaur. But we do have a few bones that are tantalizing in terms of telling us a little more about the environment. One of these is this large bone right here. This is the neck bone of a brachiosaur, one of the very large long-necked dinosaurs that we think of in the golden age of dinosaurs of Jurassic Park. But they extended up into the Cretaceous and lived with Falcarius at this site. We also have a smaller vertebra backbone of an armored dinosaur, still very large for the kind of animal it belongs to. The armored dinosaurs, the ankylosaurs, were very abundant.
The small number of other dinosaurs also might suggest something unusual is going on at this dinosaur graveyard. The site is almost exclusively Falcarius, and there is evidence of several mass die-offs. Why are these animals grouped together here, and what killed them? Utah is home to several famous dinosaur graveyards, but the Falcarius site is different. It contains, almost exclusively, the bones of a single species.
Falcarius is preserved in a site with at least dozens and probably hundreds of dead dinosaurs. So the obvious question is, why are they there? What killed them? How are they deposited there? Well, sites like this are actually quite common among dinosaurs. We actually have dinosaur bone beds, as we call them, from various countries around the world. Possible explanations might include drought, they might include volcanism, flood, some type of poisoning like botulism. So there's a whole range of hypotheses. So the way the science works from here is we go just like the forensic detectives of today. We collect all of our clues and we rule out hypotheses and we see what's left over.
Other single animal bone beds, known as monospecific sites, have been explained as herds drowned in flash floods. But this Falcarius site is not an ancient riverbed.
Another possibility for theropod mass mortalities or perhaps disease, things like botulism, bad water, poison water. You know, you have a red tide, algae blooms, releases toxins, animals come to drink, they die, animals smell those carcasses, come to feed on them, and they die. So we have a number of theropod accumulations that are associated with shallow bodies of water, and these things tend to go fetid. But the density of bones suggests something unusual was going on. Normally in nature you may find a dead animal here or there, but to have this density of animals of one species is very unusual and suggests that we should be looking for an unusual cause.
The Suarez sisters are looking for that cause. They eagerly take to their roles as dinosaur detectives.
Paleo CSI, maybe.
Yeah,
I guess.
paleo CSI.
I guess
Could be,
so.
potentially.
Could be potentially. I mean, you know, you don't ever want to just rely on geochemistry. That's one of the big things in geology. Is you never just rely on geochemistry. You always look at the
Multiple lines
rocks.
of evidence.
You have to look at multiple lines of evidence. So you
And
have
that's
to,
what we're doing here with Jim. Jim and Lindsay are studying the animal. Selena's studying the geochemistry, and I'm studying the stratigraphy and sedimentology and the paleosols.
and the taphonomy.
And the taphonomy, the actual bones themselves. And all of those will be part of a puzzle that we put together.
Back in the lab, Selena Suarez turns to rare earth geochemistry to help solve this mystifying puzzle.
The good thing about this analysis is that it's not very destructive to the bones. We only need a little bit.
By looking at the concentration of rare earth elements within the fossil, the chemistry of its environment can be determined. Each fossil contains the unique signature of the groundwater it was fossilized in.
The way we do that is by taking a piece of bone, just a little sliver from the top layer of the bone, because that's where most of the elements get concentrated. And these elements get into the bone when they're fossilized. So as the bone turns from an organic piece of matter into an actual, rock, an actual inorganic piece of matter, these elements get incorporated into the bone.
The magic of rare earth geochemistry lies in determining the relative concentrations of these uncommon elements in each fossil. The dissolved bone is next run through a high-tech spectrometer, which actually counts the atoms of each rare earth element present. It does this by bombarding the bone solution with a 6,000-degree argon flame.
What the machine does then is it measures the mass of each of those different elements that are charged now. So once it goes from that and it counts all the atoms, it gets shown on to the computer.
By analyzing these numbers, the relative concentrations of elements gives each fossil its unique signature.
What we're seeing is that the animals were probably being fossilized at different times and dying off in great numbers at different times, because you not only see differences in the rocks, the type of rocks, but also differences in the geochemistry and the conditions of the bones. Obviously, we have a huge deposit of this animal, Falcarius, in a very strange environment where you have lots of springs popping up. And it's very unusual that you see all these animals dying in some type of relationship to these springs.
The Falcarius site revealed at least 2 die-offs.
I'm standing here on the contact between the Morrison Formation, the red rocks behind me, and the base of the Cedar Mountain Formation. The main quarry has bone right from this contact up through to about this interval. Overlying this, right here is the cap rock of carbonate. We have this great mass mortality. Hundreds of animals died in this environment right here. About a kilometer away, half a mile if you will, the Suarez sisters, doing their research on these carbonate rocks, found a second mass mortality of Falcarius, our new dinosaur. This proves that there was at least 2 mass mortalities of these animals in this immediate area.
Jim thinks this stuff is Falcarius. We'll see once more of this material is analyzed.
Could the same springs that preserve these bones be the killer of these animals? That is, for now, an unanswerable question. But these hard deposits may well prove to be why these fossils exist at all.
And what we're working on is a theory that perhaps this cap rock that occurs through this area held down a skiff of sediment on this erosion surface that preserved these animals where everywhere else this age of rocks was removed. This could well be the oldest Cretaceous site in all of North America.
As with any new discovery, Falcarius raises as many questions as it does answers.
Behind us, we have the red rocks of the Morrison Formation, these red mudstones of Jurassic age. They're overlain by the more drab sediments of the Yellow Cat member of the Cedar Mountain Formation. Both of these rock units have faunal ties with Europe and actually even with Africa. However, the discovery of Falcarius shows us an animal that was only known in China, particularly from beds this old. How did it get here? Well, at this time, Alaska didn't exist. It was an island floating in the North Pacific, floating northward for a collision with a piece of Canada, and this wasn't to happen for another 15 million years or so. The only route to China from Utah was through Europe. This is where the close relatives of these animals lived. Did they originate here, or did they originate in China? That question is totally open at this point.
One of the most exciting aspects of the Falcarius find is its sheer numbers. The majority of dinosaurs are known on the basis of one partial skeleton, or even just a few bones. Dozens of partial Falcarius skeletons have already been collected, and the site promises to yield hundreds, if not thousands more.
Right to the side of me, we pulled out 400 bones in a cubic meter. That's a space about 3 foot by 3 foot by 3 foot. That's a remarkable density of bones.
This graveyard contains many well-preserved fossils in huge numbers. But to see how each piece fits together, it's necessary to look at the known relatives of the newly discovered Falcarius. Its head is most like its meat-eating cousins.
This is the skull of Velociraptor from Mongolia. It's probably the best preserved skull ever recovered. Even the sclerotic rings, the bones around the eye, are in place within the orbit. And as with other Maniraptorans, we see the plumage that these animals might have had in life, and the fur-like feathers coming down its neck.
The Mongolian desert buried some dinosaurs alive. Sandstorms preserved several oviraptors in their entirety. This provides a wonderful blueprint, as Oviraptor is the closest relative to Falcarius.
Here is a wonderfully articulated oviraptor. The oviraptors are the closest relatives to the therizinosaurs. They share a common ancestor. Falcarius is the oldest, most primitive type of therizinosaur we have. If you look at the front, the chest area, we can see that the chest is built in a very similar way. We can see the hands, the Maniraptoran hands are similar. See the shorter upper thigh bone or femur, longer lower bone or tibia fibula. This is more of a running, agile type of animal. And as we mentioned, these animals have shorter tails. Unlike the therizinosaurs, these animals are completely toothless. These may have been plant eaters as well. Finding animals that are perfectly articulated, that have been buried alive as we find them in Mongolia, are critical for accurately reconstructing the skeletons of animals like Falcarius that have all fallen apart or disarticulated.
Guided by these complete skeletons, Rod Gaston reconstructed Falcarius. His challenge was to take a pile of bones no one had ever seen before and try to figure out how they all fit together.
When we start a skeletal reconstruction, the first thing that we do is take the original fossil, which has been cleaned and prepared in a lab, and we make a research cast, which is just an accurate cast of the original fossil. And before we cast them, we need to make sure that they're stabilized for casting, which often means filling cracks with carbo wax, and also we need to make sure that the bone has been properly consolidated with glue. No reconstruction work is done on the original fossil. We take the research cast, we restore the areas that are missing. You can see clearly this big chunk out of this ilium. And when you look at the pelvis after it's been reconstructed, what we've attempted to do is restore those areas. Consulting with paleontologists, using comparative literature, casts, things of that nature from animals that are more complete, we then try and get an idea of what those missing areas look like. You can see that Andrew is doing that same process on this cast of a tarbosaur skull where he's applying epoxy putty to the missing areas.
Before this restoration can take place, the bones must be cast. The first step in creating a mold is building a clay wall around half the piece. Then it's time to add rubber.
We use a silicone rubber to make the molds with, but probably the most important thing with silicone rubber is that it does not adhere to the fossil when you take the fossil out of the mold, so therefore you don't get as much breakage or damage to the original piece. After that's done, we then apply a resin, what's known as a backup mold or a mother mold over that, and then we flip the piece over, pull out the modeling clay. We'll repeat the process again. So if everything's been done properly, we're able to pull the two rubber halves apart, pull the original bone out of the rubber, and then we end up with essentially our mold, and we're ready for casting.
To make the casts, a plastic resin is poured into the molds. Mixing two parts of the resin together activates a chemical reaction, which makes it harden. Filler and color are added to make the resulting cast lighter weight and the desired color.
And then once it's full, turn it and get all the air bubbles up to the top of it.
Once the resin has hardened, the plastic cast is carefully removed from the mold and placed in the sand to keep its shape as it cools.
After the casts are pulled out of the molds, they're cleaned, and we begin the assembly process, which on smaller things basically just amounts to drilling and pinning the pieces in, and then we use super glue, things like that, to hold them together, sometimes epoxies. The larger pieces, however, require some pre-engineering where we do incorporate steel into the pieces.
This steel is important in assembling the long neck and tail of Falcarius, and for its legs to be able to support this weight.
That enables us to weld the pieces together, providing a strong structure to put the skeleton together. At this stage, it gets really exciting because no matter how many months you've spent with the skeletal material, making the molds, the casts, the reconstructions, the skeleton always comes out a little bit different than what you think it's going to. So here we go. Andrew, you want to give me a hand putting this together? One thing that's really interesting too about putting Falcarius together, or any partially known skeleton for that matter, is that there's things that we may never know about this animal. So no matter how much research has been done on reconstructing it, we may never know whether what we've done is correct or not. So there we go.
A clearer picture of Falcarius and his environment has emerged through the efforts of Kirkland's crew. With the huge number of bones still in the graveyard, they hope many more questions will be answered.
The Crystal Geyser Quarry, which preserves hundreds of individuals of Falcarius, is really unique and rare in the fossil record. And it's supremely important because when we have all these bones, you'll notice that we have babies, we have juveniles, and we have adults. We have hundreds of elements to make comparisons across. We're able to tell about Falcarius how fast it grew, what age it was when it reached sexual maturity, if there are differences between males and females, how much variation there was in the population. These are things that we rarely get to access from the fossil record, and as a result, we're able to reconstruct the ecology and the life history of a species of dinosaur that's been extinct for over 125 million years. That's nothing short of incredible.
The amazing wealth of material at the Crystal Geyser Dinosaur Quarry means that scientists may eventually know more about Falcarius utahensis than just about any other known dinosaur.
It's remarkable. Every other specimen is a partial skeleton. Here we have hundreds of animals, babies to adults, all in the same locality, probably killed at the same time. It gives us a remarkable opportunity to study this animal.
Was Falcarius the first therizinosaur? Did they evolve in Utah or in China? Why did they become plant eaters? What attracted this strange animal to this site? What killed them off in vast numbers? Perhaps we will never know the answers to all these questions. Buried in the Utah Dino Graveyard at Crystal Geyser Quarry are still many clues. Each summer, our paleo detectives will be searching for more answers. And every year, a more complete and complex picture of Falcarius and the land that it inhabited will emerge.